First of all, I would like to thank the organizers for the invitation. Thank you all for attending my talk. In the next hour or so, I will report to you my recent work with Quoc-Hung. And the title of the talk today is also the title of a paper that we are trying to finish now. Right. So let me start with some mild introduction to just to motivate what I'm trying to do. All right, so let's look at a very simple equation, just the linear equation in the whole space Rn. And it's a linear one, and the left-hand side is the Laplacian, okay? Then under some very mild assumption on F and on the solution, you can always describe your solution as a convolution. So, and the kernel of the convolution is just the fundamental solution of the Laplace equation, right? And usually this pointwise representation is often written as U equals I sub 2 of F in the case when n is bigger than 2. And with this representation, you can differentiate under the integral to obtain that the derivative of the solution can be controlled pointwise by another potential, the so-called real potential of order 1 of the absolute value of F at any point x. All right, and when I write I sub gamma here, for gamma between 0 and n, I mean the real potential of order gamma, the so-called fractional integral. And the definition is by this expression. So for a non-negative measure mu, I sub gamma of mu is just you integrate again this measure, but there is I mean, it's a convolution with this kernel. And the point, one of the important point is that you can write this n-dimensional integral here as just one-dimensional integral here. Essentially, you look at this ratio, okay, of the mass of the measure at the point x of the ball center at the point x operator t over t to the power n minus gamma, and then you sum it up. Okay. All right. So also you can deduce from this representation formula the following fractional derivative atmos, also called is estimate in Caron space. So if you look at the difference of the two solutions, okay, and then you can control this difference by this expression. Okay, so if you take a gamma, any gamma between 0 and 1, then basically you can think of, I mean, if say the potential of order 2 minus gamma of 2 minus alpha of Fp is bounded, for example, then you get something like the Holder continuous or Lipschitz continuous of the solution. But in general, you get some constant here that depend on the value of the potential of F at the point X and at the point Y. And this, it gives you an estimate in some space. In particular, so if your potential here is in LQ, for example, then you get something like fractional superlapse space. But in general, we will say this estimate for the fractional derivative. And this estimate is uniform in alpha between 0 and 1. And then you can also do this for the derivative as well. But then the potential, I mean, the order of the potential will be lower, one order lower. And here the alpha have to be away from 1. I mean, it's not uniformly up to 1. Okay? And you can see this in the 2012 paper of Nguyen and Minchine. All right. And so that was, I mean, this is just a brief introduction in the linear theory. Well, something like this is hard to believe to hold in a nonlinear setting. However, about 30 years ago, Cuban Liner and Manley proved the following striking results in the nonlinear setting. So they consider the nonlinear equation where the left-hand side is the nonlinear operator, the Laplacian, okay, which is the divergence of this vector field. Okay. And you already seen this in the previous talk of ratio. All right, and so mu here is just a finite size measure in the periodic domain omega, and p is bigger than 1. Okay, and the result of Kueber-Land anomaly is that so if you look at a non-negative solution to this equation with non-negative measures, for example. Okay, so I'm talking about non-negative measures here. So you basically you are looking at the B superharmonic solution of this measure datum problem. Then you have two-sided estimate for the solution. You can bound the solution from below by a work potential, a truncated work potential, W1P. I will explain to you this expression, I mean the definition of it in a moment. And also by the same potential with a little bit larger truncation, plus a very small term. Okay. So this is of course sharp because this is a two-sided estimate. But at that time, the proof only worked for non-negative measure. Okay, so that is what I want to emphasize. And so here, when I write W1B rho here for rho bigger than 0, I mean the so-called Having-Mazur work potential. And this potential is often called the work potential, simply work potential. And it is defined by also by this one-dimensional integral of this ratio. But now, because B not equal to 2, so if B equal to 2, you go back to the real potential. Okay, but now B is not equal to 2, so it's a nonlinear potential, and I'm sorry that it should be 1 in here. Okay, the alpha should be 1. And in general, if you put an alpha in here, then I mean that you on the denominator here, you get a power t minus n t to the power n minus alpha p. Okay, so here I mean 1. And for size measure, one also have the upper estimate in the case when b bigger than 2 minus 1 over n. This is also in the paper Nguyen Cong in 2012, and the estimates is like this. Okay, so you have to take the total variation of the measure mu here, and you add a small term here. Okay. All right, but this is for p bigger than 2 minus 1 over n. And so that is the story for the solution, but not for the derivative of the solution. But, you know, more than 10 years ago, in a series of papers by, you know, Duza Minjuni, Kuzi Minjuni, the radiant bounds has been was obtained. So you look at the solution to the Laplace equation with measure data mu in the case when p bigger than 2 minus 1 over n, then you can control the radiant of the solution pointwise by not the work potential, but the read potential to the power, I mean the read potential exactly of order 1 to the power 1 over p minus 1 plus a small term. And the I sub 1r here is just a truncated read potential up to level r here. All right. And I should say that historically, the nonlinear case, but would also be equal to, were done in the chain paper of Minjuni. But for the case when p bigger than 2, it was done in the paper of Duza and Minjuni. But in that paper, they used a larger potential, exactly the work potential, but the order here is 1 over p. So you see n minus 1 in here. So the point is that you bring the power, I mean the exponent 1 over p minus 1 inside the one-dimensional integral. So for the read potential, I mean, in this case, this exponent is outside. So when p is bigger than 2, this is smaller than this one. Okay. And also, Pointwise fractional derivative bound for the Laplace equation with measure data in the case when p bigger than 2 minus n are also available, and I will discuss about that later. Okay. And recently, radiant estimates has been extended to the case when p is below 2 minus 1 over n. In particular, when p is above 3 times n minus 2 over 2n minus 1. First, by using a work potential in our work with Quoc-Hung, and then by the read potential in the recent work of Hong Ji-dong and Zhu. And so the natural question is to consider the remaining case where P is below that, 3/2 exponent, 3n minus 2 over 2n minus 1. And that is the main goal of this talk today, okay? And as 3n minus 2 over 2n minus 1, here is smaller than 3/2. So it is enough to consider the case when P is smaller than 3/2, so that's easy to say, okay? So the bound here is actually independent dimension. So we just look at this case. I will report only this case, and actually if you can do this case, you can do everything, all right? So I only focus only on this case when P near 1 and up to P 3/2 here. And as reviewed from the work of Nguyen Cong Phuc and his collaborators, an important technical tool in the study of gradient estimate is a comparison estimate that connects the solution of the measured atom problem to a solution of a homogeneous problem. So let me make it more explicit. So you look at a solution, U, say in W1P local of the measured atom problem minus delta Laplace P minus the B Laplace of U equals mu. And then you take a Q, okay? So that the double of that Q is also inside your domain. And then you look at another solution, W, okay? And W is solving the homogeneous problem, and the boundary data W is U on the boundary of the Q, okay? All right, and then so on the boundary W is U, but inside the Q, W is very good. It's a it's a solution to the W is a solution to the homogeneous problem. So we know a lot about W because we have C1 alpha estimate. I mean, in this case, we have C1 alpha estimate for W. So if we can find a way to quantify the difference between W and U, then we will have a lot of results. I mean, there will be a lot of consequences from that. And let me tell you the difference between the derivative of U and W in the next lemma. So in particular, in the case when P is bigger than 3n minus 2 over 2n minus 1. So this is what I call comparison estimates, okay? So assume that P is bigger than 3/2, then you can quantify the difference between U and W in the following ways, okay? For some power kappa, okay, for some positive power kappa. If you look at this integral here, I mean the average over this Q, okay, that you are solving your equation here, okay? Then this is controlled by the total mass of the measure over that Q, over this this length of the Q, r to the power n minus 1, and then there is a power 1 over p minus 1, plus another term, okay? And this term will also depend on the total mass of the Q, and also on some L kappa of U, okay? So of course, if your mu is 0, you don't see anything, okay? Of course, if your mu is 0, then W is 0. And in the case when P is bigger than 2 minus 1 of n, the kappa is chosen to be 1. The kappa is 1 in that case. And actually, when P is bigger than or equal to 2, you can just drop this term, okay? The second term here can be dropped, okay? But in the case when P is smaller than 2, you need this tail here, okay? And this tail will depend on the norm of U in a very small norm, L kappa, okay? And in that case, you take kappa to be 1. But when P is smaller than this ratio 2 minus 1 over n here, then kappa has to be, kappa has to be smaller than 1, and it's okay as long as you can take kappa to be below n times b minus 1 over n minus 1. Basically, the reason is that if you look at the fundamental solution to the Laplace equation, then to the Laplace equation with to the Laplace equation, then the fundamental solution is in the weak LQ, and Q is exactly this number. So you shouldn't expect that you can go above this one. Okay. So you see, when B is getting smaller and smaller, then the integrability of the derivative is getting smaller and smaller, and then it's harder and harder to get this kind of bar. And our main contribution is just this comparison estimate for small b. Okay, in particular, I will talk only the K1P between 1 and 3 half. And here we're going to use kappa to be small number, say p minus 1 squared over 2. Okay? And of course, this number is always below this threshold. Okay. And so this is our recent result with Hung. And so when p is between 1 and 3 half, and for this kappa, we have this exactly comparison estimate. And of course, you can replace kappa with any smaller number. Okay, but somehow in our proof, we're not able to get it up to this threshold. But for application, it's okay with this kappa. Okay, maybe if we work harder, we can get up to this theoretical exponent. But for our application, I mean, a small kappa would be fine. Right? So that's basically our main contribution. And so now let me tell you some consequences of this. Or maybe first let me give you the proof of this, and then I will tell you the consequences. And okay, so I want to first make a remark that we also have a comparison estimate for the function. Okay, for the function. So for the function, you have this. I mean, for the side length of the Q, you got the power r to the power the r to the power n minus p. Okay, and then you have this L kappa norm of U, but you can subtract a constant here. And actually, because you can subtract a constant here, let me explain to you that later on, when you try to bound pointwise for the solution, you can use the work potential. But for the gradient, because you cannot subtract a constant here, in the end, you have to use the read potential to bound for the pointwise bound. But I will do that later. Okay. All right. So maybe let me say a few words on the idea of the proof. Okay. So let's see. Well, I will not go to the technical detail. I just want to say this, the main idea. Okay. Just to convince you that it should work. Okay. The first step is that we bound. Okay. What is the main difficulty? The main difficulty is that the difference U and W is not in the sublet space, okay? Because it's not it's not in L1, okay? It's not in L1, so it's not in the sublet space, okay? So the first step is that we can use just the one-dimensional sublet inequality, okay? One-dimensional, and the one-dimensional is applied in the last variable. So you are in the setting of, n dimension, right? And then you apply basically the sublet inequality only in the last variable. And then if you do that, you go over some of the classical, stuff for the comparison estimate. You try to use sublet inequality in only the last variable, then you get this bound. And this triple norm here, okay, this triple norm here. So these are just the same, right? Only this one. This triple norm here, when I write this, I mean that it's going to be in the last variable, it's going to be in L2 minus B. And then in the remaining variable, it's going to be in this norm p minus 1 times 2 minus b over 3 minus b, okay? And so I use a triple norm here just to mean that I normalize everything, okay? I take the average on every direction here, okay? I take the average on every direction here. But you can, so it's just a standard, mid norm, but then I take an average on every direction. All right, and so you see that when b near 1, this could be large, right? When b near 1, it could be large, it could go to 1, but it's just one in one direction, so it's okay. However, when b is large, this is very small. B minus 1 is very small, right? So when b is large, in the last variable, it could be large, so it could be the problem. But on the other hand, for the remaining variables, it's very small, so we okay. But we have to prove that, right? And in the second step, we prove that. We show that this quantity here is subcritical in the sense that we can show the reverse Holder inequality for this quantity. And we can actually bound it by exactly the kappa norm. And kappa is a very small number. There's some error term, but this error term you can always absorb into this, so you are okay, right? And in fact, this also holds for a quantity like this. So LS in the last variable, and I mean S1 in the last variable, S2 in the remaining variables, but you need to have that S1 smaller than P. But S2 has to depend on S1. S2 has to be smaller than this expression. It depends on S1. So S1 can also be, bigger than 1. S1 can also be bigger than 1. But then S2 has to be small. Then you're okay. And then you combine the last two, the previous two steps, you get the result. So that's the main idea. But you have to work a little bit to get this one. But that's the main point. Okay. All right. So so let me talk now some consequence of this. Okay. The first consequence is that we will get from this comparison estimate, we can get a sublinear Poincare inequality with an error term. So if you look at a solution of the, beta plot equation with measure data mu, okay, then in general, we know that the Poincare inequality fails when the gradient is below 1, right? But if you work with a solution of a measure data problem, then you're okay. And you can bound, this oscillation here by the L kappa norm of derivative solution plus some small error term here. And yeah, so basically from here you see that if you get anything for the solution, you can also get it for the derivative. You also get it for the solution because of this Poincare type inequality. I mean the sublinear one. And I forgot to say that in our comparison estimate, the Q here is larger. Okay, the Q here on the right side here is larger. So the original one here, you can use just one Q. Okay, I mean the same Q on both sides, but we have to use a larger one here. And I told you the reason is that in the first step, we use the same Q, but then we have to use a reverse Holder. So it's going to be larger in the second step here. And that's why we have to enlarge the Q, okay, in our comparison estimate. But that's harmless. That's harmless in application. All right, so now, well, for the remaining of the talk, I would say that I will rely most of the result on the work Minzuni and collaborator. So I wouldn't say this is our contribution, okay? Our main contribution would be just comparison. For the rest, is that because there is a machinery that was done by Minzuni, Duza, Kuzi, and so you just try to get their result, read their paper, plug in the comparison estimate, then you get something. Okay. So the first thing is that we will be able to extend this Pointwise estimate up to 1 now. Okay, so and we still can, for the derivative, we can use the real potential, and then we get the power 1 over b minus 1 here, plus a small term. Of course, you can always take the kappa to be as small as you want because of the reverse Holder inequality. But I will always choose my kappa to be b minus 1 over b minus 1 square over 2. You also have this this power for the solution with the work potential, and I told you that we cannot use. I mean, we can use the work potential here. The reason is that one of the main reasons is that we can subtract a constant here in the comparison estimate. Okay, and so we can use actually a smaller potential. Remember that in the case when b is smaller than 2, this potential is actually smaller than I mean, this potential is smaller than the one that you take out the power outside here. I mean, I sub p to the power 1 over v minus 1. But for the radiant estimate, we cannot subtract a constant, so we have to use the real potential instead of the work potential W1 over PP, okay, that I mentioned earlier. Okay. And so now the theory works for all P because of the reverse of ratio and heat collaborators. Okay. And for the rest of the talks, you know, I want to extend the result of Uzi and Mizuni to the K when P near 1, but I would say that most of the works were done by them, and we just, you know, try to plug in and get the result from their argument. There's some twist that we need to take care, okay, because we are working below 1. So when you try to look at the oscillation, for example, you have to measure the oscillation. Say you have to measure the oscillation in terms of something like this. You cannot use the mean of the solution, because the solution may not be in 1, for example, or the rate of the solution may not be in 1. So you have to use expression like this in the process. But everything we will find if you look at the paper of the Vaughan Shapley, and then also this kind of quantity has been used recently in the work of Hong Chi-dong and Zhu, where they try to get the sharp bound in the case when B is bigger than 3n minus 2 and 2n minus 1. Okay, so but anyway, let me just describe it, okay, because I still have a lot of time. So the first thing is that the fractional derivative for estimate for the solution. Okay, so again, you look at this equation, the Laplace equation with measure data. Say b smaller than perhaps, and I told you the k when b bigger than 2 minus 1 over n has been done in the work of Uzi and Minzoni. Okay, then you can control the difference of the solution at any point x and y in a smaller ball. Okay. Okay, by this expression. So you get x minus y to the power alpha here, and then you get the constant here. But the constant is just the value at x and y of the same function, And the function here is the truncated potential. I mean, work potential order 1 minus alpha times b minus 1 over bp. You have also a small term here, okay, the error term here. And this is the point that this is uniformly for all alpha between 0 and alpha tilde, but you have to assume that your alpha tilde is strictly less than 1. Okay, so basically you can think of this as the endpoint estimate of this result, because say when alpha go to 0, you will basically get back to this Pointwise estimate. Okay, in general, you get the Caron space estimate up to order alpha tilde uniformly, but you have to take alpha tilde to be smaller than 1. Otherwise, you would get this. With the work potential W1 over P, which is very strong, and it may not be true. Okay. And so here I stated theorem for the Laplacian, but if you want to state this for the more general equation with a nonlinear structure, like general nonlinear structure, for example, then you need some condition. So if you want to go all the way to 1 here, then you need a small b multi condition. I don't want to go into the technical details here. Now, if you don't assume the small b multi condition, so you only assume measurability. Okay, if you assume only measurability, then the alpha tilde here has to be below alpha 0. And alpha 0 here is exactly the maximal de Holder continuity exponent for the equation with measurable coefficient. Okay, so you still can do with measurable coefficient, but your alpha tilde has to be small. Okay, so that is for the solution. Now, what if you want to go up to 1, including 1? Okay, so what if you want to get something like this? Okay, then you have to change the potential. Okay, you have to change the potential. So again, under the same assumption, you have this bound, the difference of u x and u x and gy, and then you got x and y to the power alpha. But now alpha can also be 1. Okay, uniformly from 0 to 1. But in this case, you have to switch to a small, the larger potential. So the potential the truncated grid potential of order p minus alpha times p minus 1. Okay. Those are the same function, but usually at the point x and y in here. The power here is 1 over p minus 1 outside. Now, if your alpha is 1, okay, if your alpha is 1, okay, then you get exactly I sub 1 to the power 1 over p minus 1, and then you get back to this estimate for the gradient. So, but I still don't understand it. There is some gaps in here. It's maybe, I don't know if this is a natural phenomenon or it's just some discontinuity that we don't understand. So, at this point, I don't find any estimate that give a connection, an interpolation between 0 and 1 in a smooth way. Okay, so if you want to interpolate at 0 in a sharp way, you have to use the Bob potential. Otherwise, you use the real potential, but they not. I don't know if anything there is anything in between. Okay? In the K when B smaller than 2. All right, this also holds for equation with general nonlinear structure, but in this case, we have to assume a stronger assumption. We have to assume some kinds of linear V multi condition. Okay, and described in the work of Razzo and Kuzi. Right. So I don't want to go into the technical details here. All right, and what else do I want to say? Yeah, so you can also do this for the derivative. Okay, now up to b, up to 1. B can go up to 1. So in this case, you have to use, the difference of the radiant here, you have to use the grid potential of order 1 minus alpha. 1 minus alpha. The alpha here is uniformly between 0 and alpha tilde, but alpha tilde have to be below beta sub 0, and the beta sub 0 is the maximal exponent in the C1 alpha regularity for the homogeneous equation. The B Laplace of the B Laplace equation. Okay, and if you try to work with equation with more general nonlinear structure, then you need another stronger condition, the so-called linear Holder condition. Okay. All right. So let me just mention here some of the main, some of the estimate that give rise to those results. Okay. So one of the important estimates is that you can control this, some sort of truncated fractional maximal function of the derivatives here. But here you don't take L1, you take LK here, kappa here, and kappa is small. And this is controlled by also the fractional maximal function of the measure mu with some degrees here, plus some error terms in here. And this whole uniformly up to 1, but not including 1. Okay. And if you want to do this, if you want to control this fractional maximal function here up to 1, then you cannot use just this expression. You have to use a larger one. You have to use the real potential of order 1. And this is, I mean, of order p minus alpha times p minus 1. Okay. And then you can do it. And it will hold uniformly up, I mean, from 0 to 1. Okay. But of the same expression here. And now if you want to do it, of course, if you have this for the function and for the derivative, then you also have it for the function because of the Poincare inequality that I mentioned to you. Okay. And also, you also have the oscillation estimate for the derivative. But because, as I mentioned, you cannot use L1 in this case. So you have to use L kappa, and kappa is below 1. So you have to use expression like this. Okay, you take Q, where Q is the vector, so that it minimize this integral average. Okay, then you multiply by, and this is some sort of the fractional sharp maximal function. Okay, the truncated fractional sharp maximal function, and then you can control this by the fractional maximal function of mu plus a potential plus a small term. And then I want to mention that this kind of, this kind of expression has been used in the recent paper of Hong Yidong and Zhu when they try to estimate for the Pointwise estimate for the derivative. And this is uniformly up to beta 0. Okay, only. Okay, so next I will tell you about global estimate. Okay, say global estimate in the boundary domain. Okay, assuming some good condition on the boundary. So if we work with a C1 linear domain, okay, and if you work with the normalized solution, okay, we like to work with the normalized solution because it behaves very well. It behaves very well at the boundary. Okay, then for small p, then we have this Pointwise estimate for the solution. This is true for all x inside the domain. Okay, and you truncate at the level, at the level 2 times diameter of your domain. Okay, at any point x. And this is very neat, very neat. But however, it does not capture. Because we work with measure data, so it doesn't capture. Here it doesn't capture how it goes to 0 at the boundary. We just see this. It's not sharp at the boundary, but it's good enough for model purposes. And Dong and Zhu obtained this result in the case b bigger than 3/2. However, this global estimate is still unknown for equation with general nonlinear structure with linear or Holder coefficient. Okay, it works if you put some mild structure there with some coefficient there, but if you put a very general structure there, at this point, the reflection argument doesn't work, and it's still unknown. It's still not clear to us how to do it for general structure. Okay, so I stay this for just the Laplacian. Okay. And that global Pointwise bounds up to the boundary here can be used to study the Riccati equation with a sublinear rho in the gradient. And so if we look at this, so suppose that you have a measure, and the measure is good in the sense that it is controlled by the capacity. And the capacity is the capacity 1s, and s is its power. So I assume that my q is smaller than 1. My p is smaller than 1, but it's bigger than p minus 1. Okay, bigger than p minus 1. And then you look at this equation. It's where we have equation with measure data, and then we have we have a term here, and the term is the grade of u to the power q here. Then this condition, we imply, I mean, for small c0 here, we imply that there exists a solution to this equation, and the solution also behave, I mean, the gradient of the solution also behaves similarly. The point here is that q can be below 1. In the case when q is bigger than or equal to 1, this was done in our work, but we were not able to get it in the case when q is more than 1 because of the lack of convexity. But with the Pointwise bound here, we can do it. In the previous work, we use weighted bound, and with that weighted bound, there is some lack of, I mean, we try to apply the Sauder-Fixed point theorem, and then we have some lack of convexity, and we get stuck with that. But when we get a Pointwise bound, it's okay. We can go below 1, and now the problem is completely solved. Okay. All right, but only for good. I mean, for good coefficient. I mean, for good structure and for good domain. All right. And this capacitory condition here is sharp, at least for non-negative measure compactly supported inside the domain, because this is also a necessary condition in that case. And I'm using the S capacity, I mean, that's the non-homogeneous version of the S capacity here. Okay. Where S is this exponent Q over B minus 1 plus 1. All right. And okay, I have 10 minutes. So the next thing is that I want to talk about global weighted estimate for the gradient. In many applications, for example, in solving the refractive time equation with the linear row cube, okay, it is enough to use a weighted estimate for the gradient. And in that case, we can work with equation with general nonlinear structure under a much weaker condition on the coefficient and on the domain. And explicitly, we have the following Nguyen-Cong type bound for the gradient of the solution. Say, suppose that P is below 3/2 and Q is bigger than 0. Then for any infinity weight and for any renormalized solution to this measure data problem, we have this weighted estimate. So you can control the derivative of solution only on any LQ space with the weight W and where the weight is in infinity class. And you control by the fractional maximal function of order 1. Okay. Under the assumption that the nonlinear structure here satisfies a certain B multi condition, small B multi condition, and the domain is sufficiently flat in the set of drivable. And previously, this is known only in the case, I mean, in the case P bigger than 3/2, basically, okay, in our previous work. In the case when P below 3/2 here, we have some result, but in that case, we have some restriction on Q. We have to ask that Q is bigger than 2 minus P, and then we have to ask that W is some AQ over 2 minus B class. Okay, would be very, if it is a strong restriction, then the infinity class. Okay, and yeah, so the M1 here is just the fractional maximal function of mu, and it's just defined by this supremum. Okay, and this is smaller than the real potential of order 1 that we used earlier, but I mean, actually, this is basically equivalent. Okay, if you put I1 here, it's still the same because of the Nguyen-Cong time bound. So you can, I mean, whenever you have infinity weights here, it looks smaller than the K when you replace M1 by I1, but basically they are the same. Okay, because of the result of Nguyen-Cong with that. And this is the definition of the infinity weight. This is just the union of all the AB weights. And another way of saying it that you can control the ratio of, I mean, you can control the measure of any set by basically you can compare this measure to the Lebesgue measure in some sense. Okay. Okay. So I guess I finished early today, a little bit early today, and so thank you very much for your